Hello everyone, welcome back to the latest lecture session. We've been discussing about different wastewater quality parameters we are going to encounter in this course. First and foremost is BOD, biochemical oxygen demand. In that context, we looked at measuring BOD and we looked at some of the different scenarios you would come across, right. Let me just summarize that. One case is when we have very low strength wastewater, let us see. So, I can just say the BOD is equal to DO initial minus DO final and get it, but DO final can't be less than 2, then I can't get reliable measurements. So, when the wastewater is high strength, how do I do it? What am I going to do? I am going to dilute the wastewater, right, by dilution water. This is the dilution water, and only a fraction of this is going to be my actual sample or the wastewater. So, what is the approach here in this case? We know that the volume of the mixture total here into BOD of the mixture. What will this give me an idea about? Volume into BOD, let us say again milligram per volume or mass of oxygen demand per volume. So, it will give me an idea about mass of oxygen demand or the organic content, let us say volume cancel out. What is this going to be equal to? It will be equal to the organic content in these two parts. So, one part is volume of the dilution water into BOD of the dilution water plus the other part volume of the sample into BOD of the sample. So, typically what will we have? We will measure this. We know volume of the mixture is typically 300, we know how much wastewater I am adding or you are adding, and we know the difference to be VD, and BOD of the mixture is what you are measuring, and BOD of the dilution water also you will typically measure, and thus you can get this particular unknown, which is your BOD of your high strength wastewater, let us see, right. So, that is one aspect to keep in mind. So, technical aspects, and let us say if I sometimes want to estimate the BOD without measuring it, let us say I am short of time, but I just want to run a quick test based on the data that I already have. What do I do? As in, I do not want to run the BOD test, but I want to estimate it. I develop a model to try to explain and predict the behavior of the system. So, how do I go about doing that, right? Again, assuming that I know the different underlying variables and constants, and I can make some reasonable assumptions. I want to be able to explain the system, right, as in if the BOD right now is so and so, and if the temperature is this, assuming a rate constant of x, I am going to see this BOD at the end of 5 days or 10 days or 3 days. So, how do I do that now? So, again the whole aspect is based upon applying mass balance, let us see, right. So, let us just see what we have out here. So, in this BOD test, what is it that I am assuming? I am assuming that the organic contents are going to products, and the assumption here is that it is going to be done by microbes or being catalyzed by the microbes in the presence of oxygen, and the assumption is that this is a pseudo first order loss. Again, this is valid when the dissolved oxygen content or DO is greater than 2 milligram per liter, right. Otherwise, microbes will not thrive. Again, this is the case, and let us say the K is the rate constant, and to use the usual nomenclature, L is the concentration of the organic content. So, initially I have L naught, okay, L naught, this is not L out. So, in my sample, let us say I want to be able to estimate it, okay. This is my sample, this is a closed system, meaning it is a batch reactor, right. I want to estimate or predict the behavior of this organics, and please note that I am applying the mass balance on this organic content, and this is a batch reactor. What is the mass balance equation? V dC by dt is equal to mass coming in Qn Cn minus mass going out Q out C out plus volume into rate of formation minus rate of loss. Here it is a batch system, so no mass coming in and no mass going out, and volume cancel out. and also here organics are not being produced, as in the waste or our waste or the waste in that particular sample is only being degraded or being lost, it is not being formed. So, rate of formation is 0. So, dC by dt is equal to minus rate of loss. So, for first order we know that it is equal to minus the rate constant times the concentration of the organics, not organics, concentration of the reactants. Here we have only one reactant, which is the organics, and we are saying that the concentration of the organics is being represented by L. So, this is also not C, dL by dt. So, integrating and so on and so forth, LT is going to be equal to L naught into e power minus KT, right. So, what will this give me an idea about? If this is the initial organic content, this will give me an idea about the organic content after time t. But if I am trying to measure the BOD, so what is it I have? I have the organic content at time t being equal to L naught into e power minus KT, right. But I want to measure the BOD. What is BOD? It is the biochemical oxygen demand, pardon me, biochemical oxygen demand, and let us say 5-day or whatever, or at particular time t. So, it is the difference between the initial organic content and organic content after time t. So, the oxygen demand or the oxygen is consumed by the microbes in bringing down this organic content from L naught to LT, right. So, we are, when we say we are talking about BOD, it is the initial organic content minus the organic content at time t. So, BOD at time t is equal to L naught into 1 minus e power minus KT, right. So, that is something for us to keep in mind. So, if I know the estimate for the organic content, so here there are two aspects to keep in mind. L naught is the initial organic content, right, initial organic content. But how do I measure L naught? Typically I am only measuring BOD 5 or after 5 days. But as you know, within 5 days not all the organic content is going to be consumed, but I want to be able to what do we say, measure the or all the organic content or ultimate organic, ultimate BOD. Why do I say ultimate? Because we increase the time to a consumable value BOD ultimate. What will that turn out to be? Let us say time equal to infinity, let us say, right, ultimate time, a lot of time, then BOD ultimate will be L naught, that is what you see, BOD ultimate will be L naught. L naught is the initial organic content, or if I measure it in terms of BOD, it is going to be equal to ultimate or called ultimate BOD. And assuming let us say a rate constant is more or less same for a particular kind of wastewater at a particular temperature, I can get an estimate for K, and after a particular time BOD 3, 5, 10 or such, I can calculate the BOD, let us say, right. So, that is the principle out here. What did we do? We just applied the mass balance. So, let us just have a quick recap. So, modeling BOD decay, what is the control volume? It is my BOD bottle, the 300 ml BOD bottle, right. We are applying mass balance on the organics in the bottle, applying mass balance, this is what we have, and I guess we already talked about these aspects. LT is the amount of oxygen demand remaining or the amount of organic content remaining after time t. Again, please note that we are when we are talking about organic content in terms of the experiments or our calculations or measurements, we are measuring it in terms of oxygen demand. So, LT is the amount of organics remaining after time t or the amount of oxygen demand remaining after time t, and other aspects we already or I just mentioned. So, this equation obviously simplifies to this particular equation, right. Batch reactor, I end up with this, and we need the BOD at time t, which is the organic content that has been consumed or degraded by time t. Yes. Thus, BOD at time t equal to L naught minus LT, that is equal to L naught into 1 minus e power minus KT. So, I just drew this graph, and the rate constant I took was a typical rate constant for decay, right. KD is equal to 0.3 day inverse, and initial organic content or the ultimate BOD is 200, that is why you see 200. Initial organic content or ultimate BOD, I am measuring it as or with, not measuring it, I am indicating it here, 200, I took it to be 200. And so, here we have the test time in days, organic content remaining, and also BOD in units of milligram per liter of oxygen. So, BOD test I started here at 0 day, right, and I see obviously with time what is happening, some of the organic content is being degraded. When I say organic content is being degraded, some oxygen is being consumed, so that is why the BOD has increased. So, let us say at 5 days it ends up being the BOD is this. So, what happens to the organic content in this meantime? Organic content is the green particular legend. So, I have this organic content was initially 200 and the organic content keeps on decreasing because the microbes are degrading it in the presence of oxygen, and after 5 days obviously I only have a little of the organic content left, let us see, right. So, that is for you to be able to understand. Obviously, if I run the test for longer, more of the organic content is going to be used up, and after some considerable number of days this BOD consumed will be equal to the initial organic content. That is why we are calling that initial organic content as BOD ultimate, and at BOD ultimate measurement day, how much organic content will be left? No organic content will be left, right. So, that is something for you to be able to understand. So, if BOD 5 of a waste is 102 milligram per liter and BOD 20 which we are saying corresponds to ultimate BOD is 158 milligram per liter, what is the rate constant, right. So, we know that BOD 5 is equal to the difference in the organic content, meaning initial organic content minus organic content after the 5 day period, or it is equal to L naught into 1 minus e power minus k t. So, I have this BOD 5 is given here, time is 5 days and L naught is given as 158. So, I have to calculate k. So, this is not a great way because we have only one sample, but still for approximation that is not a bad way to go about it, right. So, I plug it in and I guess the k turns out to be 0.1 day inverse, let us say, or per day, right, pseudo first order rate constant. So, temperature dependence, as we mentioned, rate constant is going to be dependent upon temperature. As temperature increases, the metabolism of the microorganisms increases, thus rate constant of degradation of organics also increases. But it is not as if I increase it to 100 degrees centigrade, it is going to what do we say, ramp up the kinetics, right, because you are going to have the death of microorganisms after a certain threshold. So, obviously, we are talking about certain thresholds here, right. Empirical approach again quite widely used, rate constant at temperature T is equal to rate constant at 20 degrees centigrade into theta to the power of T minus 20, and different what do we say values for theta. Typically, these will be given in the formula sheet, you do not need to mug up all these aspects now, right. The point is to not mug up aspects, but to understand the principles and the working of the system. And the rate constant for the degradation of organics in the BOD test K was determined empirically to be 0.2 day inverse, right, at 20 degrees centigrade. So, if I increase it to 25, what will the K be? If I decrease it to 10 degrees centigrade, what will the K be? Why is this relevant? I mean, this information that we are going to gain by solving this. Why is it relevant? As I mentioned, in the summer the degradation kinetics is going to be faster, right, and in winter or even in the colder regions, right, you are going to have relatively low kinetics, let us say, or slow kinetics, pardon me, right. Let us try to see. So, it is just plugging it in. So, we are not going to spend much time. So, K at 25 turns out to be 0.26, when at 20 degrees it was 0.2, and at 10 degrees what is it going to be? It decreases greatly though to 0.056. I think I have a graph out here, right. I have this graph. So, L naught ultimate BOD, it is with 200, right. At 20 degrees centigrade, this is what we have. I think I took 0.3 or 0.2, does not really matter now. I think I took 0.2 rate constant. So, at 25 we see that it did increase, but not by a lot, right, but it does, there is increase. But when I decrease the temperature, you see that there is a remarkable decrease in the consumption of the organic content. So, you can see that the degradation kinetics are going to be remarkably affected at relatively low temperatures, let us say, right. So, that is something to keep in mind. And organic content remaining, obviously if this is just representing this graph in a different way. So, if it is at 20 degrees or 25 degrees centigrade within 5 days, let us say 50 by 200, right, considerable fraction, I guess 75% is consumed, right, but at 10 degrees not much, let us say, right, at 10 degrees centigrade not much has been consumed, very little has been what do we say consumed, and a lot of it is still remaining out here. Again, let me not spend more time looking at the same aspect. So, what are the effects of waste being discharged into a river? We discussed this briefly earlier, but I believe I have a decent picture out here. What happens to river water quality during various mass bathing festivals or events? For example, we have Kumbh Melas here, and you are going to have a lot of organic content, flowers being dumped, or people immersing stuff or having a bath. So, during that time again a lot of organic content comes into the river within a short period of time. Though we say that the rivers are holy, we do not let them be pure, right, we do not let them rejuvenate, and again there are other issues, obviously I am not going to go into that aspect now. So, downstream of Delhi remarkably highly polluted streams join river Yamuna. Where will the river quality be acceptable with respect to DO again, right? Two questions. Again, how will we model it? Obviously, look at this, if this is the river and this is the waste coming in, and assuming perfect mixing, understand that the concentration of the relevant compound, dissolved oxygen or BOD, is changing with X, meaning we are going to use plug flow reactor either with or without dispersion. So, that is the best way to look at it, let us see, right. So, here we have an example, we will just look at the holistic picture or take a holistic view and move on. So, here I have my stream coming in, so upstream of that my dissolved oxygen is pretty good and the BOD is or the organic content is very low. So, thus the aquatic life or aquatic system ecosystem is thriving, let us say, but right at the point of mixing, so BOD is very high in my particular wastewater. So, the organic content in the mixture of the river and the wastewater takes a huge jump. DO does not fall immediately, right, it will decrease but will not fall immediately. But now what is going to happen, the DO is going to start decreasing. Why is that? Because the microbes are going to degrade this organic content in the presence of oxygen. So, the organic content is going to be decreased, right. We looked at this graph earlier, right, or even here if I want to dl by d theta is equal to minus k L, let us say, right. So, L at theta equal to L naught into e power minus k theta. So, you see exponential decay, that is what you see out here. But with respect to DO, what is going to happen? Obviously, it is going to decrease because organic content consumption or aerobic degradation takes place. And then you can have septic zone if you do not take care, right, you can have anaerobic conditions. But in the meantime, you are also going to have replenishment of oxygen from the atmosphere, right. So, that is why again you are going to have an increase in your what is this dissolved oxygen. So, I am concerned about this stretch probably when the conditions are so poor that the aquatic ecosystem will not thrive. So, these are the aspects I need to look at, let us say, right. Let us move on. So, as I mentioned, COD relatively faster and relatively more reproducible, unlike the BOD test which is slow, and depending on the kind of waste and whoever is doing it, let us say, you are going to have issues with respect to reproducibility, right. COD though not really such an issue, but it is relatively costly, right, because the ingredients are costly, but one aspect is the amount of lab space required is pretty much less, right. So, COD of the waste is measured in terms of the amount of dichromate Cr2O7 2 minus, let us say, which is reduced or is used to oxidize the sample during 2 hours, right, your 2-hour period in a medium of boiling and acidic conditions, let us say, right. And in the presence of AgSO4 catalyst, sometimes you also add mercury, Again, we are going to look at this reasons later, let us say, right. Mercury add to, I believe, complex the chloride so that it is not oxidized by Cr2O7 2 minus. Again, AgSO4, I guess we are adding it for what is it now, as a catalyst, let us say, right. So, stoichiometry, you can look at that. COD is faster than BOD, that is something that we already knew, let us see, right. And again, both biodegradable and non-biodegradable, but one aspect is similar to the CBOD test. Even the COD test will not oxidize or lead to oxidation of your ammonia. So, that is something to keep in mind though, right. So, we have spent considerable time on oxygen demanding material, but that is worthwhile because during water and wastewater treatment we are always concerned with oxygen demanding material. Let us now look at nutrients. When I say nutrients, I am specifically concerned about nitrogen and phosphorus. Firstly, nitrogen and phosphorus, how do they come into the picture? So, nitrogen, let us say we eat protein for muscle growth and such, right. Now, 6 packs, 8 packs and what not are in fashion now or in vogue, but in general even for muscle retention, if not for growth, you need to take in proteins, let us say, and amino acids and such. So, you are going to have sources of nitrogen, and similarly we have different sources of requirements for phosphates now. So, I am going to consume it, and obviously some of it is going to be coming out of my particular system or my system, and that is going to be present in the wastewater. So, if I need it, also understand that other what do we say, beings will also require it or will thrive on it. The issue with nitrogen and phosphorus is that all the other nutrients are typically present, let us say calcium, magnesium and such, but nitrogen and phosphorus are limiting nutrients. They are not typically present in abundance in the natural waters. So, if a wastewater comes into play and joins that particular natural water, let us say ocean or let us say inland water bodies, surface water bodies, what is going to happen? You have all the ingredients required for explosive growth of your algae, let us say. So, you are going to have algal bloom or explosive growth of algae within a short period of time. So, after this particular bloom, what is going to happen to this algae? When there is no more, what do we say, nitrogen or phosphorus or any other nutrient, they are going to die. When they die, they are going to increase the organic content of this particular lake or river, typically lake, right, because it is relatively less turbulence, no flow of water, and then you have decaying organic content. So, again oxygen content in that particular lake will be very low, you will have septic conditions and so on and so forth. So, thus we are typically concerned with nitrogen and phosphorus. Inland, phosphorus is the limiting nutrient, and in oceans nitrogen is the limiting nutrient. That is something to keep in mind. Let us just look at that. So, this again I give the relevant reference out here. This is from China. Obviously, I am just looking at good pictures out here. So, we see people having fun, right. I mean, seems like a good day to be out and people are having fun. And here is the bigger picture, right. We see the people having fun out here, and you see that this is nothing but an algal bloom from 2013 though, right. You see the scale and the extent of this particular algal bloom. So, though in this picture seems like some people are having fun, I am sure at the end of the day some people might have what do we say, observed, not sure, let us say the probability is very high, observed remarkable adverse effects, let us say, because we will come back to that. So, microscopic plant like organisms, right, algae, photosynthesis again, thrive on excess nutrients, as I mentioned, nitrogen and phosphorus. Where are they found in? They are found in fertilizers and also in our wastewaters and such, and they make their way from backyards, fields or septic tanks, and they lead to producing or lead to algal blooms that can sometimes be seen from space. We will look at that. As I mentioned, these blooms can create dead zones or areas that are deprived of oxygen. Some algal species, as I was just about to mention earlier, can produce toxins that can wreak havoc on human livers and neurological functions and can cause seizures in marine mammals, let us say. So, typically again we have issues not with just the aquatic ecosystem. When I say just, it is because I am selfish, primarily selfish, but concerned citizen, I guess, right. So, humans also have considerable or can experience considerable adverse impacts, let us see, right. So, as I said, we can see it from space. This is from North America. These are the largest lakes in the world. I think we are talking about Lake Erie. North America, this is 2012, but this is always the picture. You can see algal blooms, right, algal blooms. Anyway, you can see the algal blooms all out along this coast, and in this lake obviously all along this coast, right. So, caused by agricultural practices, as in we add urea, right, we need to add nitrogen and phosphorus in different forms for our plants, and sometimes we dump excessive what do we say fertilizers, and you have rain, and then runoff from this agricultural land ends up in the lakes, right, and that is going to lead to algal bloom, right. Again, not all algal blooms produce toxins, but for those that do, in fresh water systems the culprit is usually the bloom green algae or cyanobacteria, right. Again, they are very harmful to your liver. And again, neurotoxins that can shut down a person's heart or stop their breathing or cause them to lose their short term memory or send them into convulsions. These are common toxins, I guess, right. So, again, even though I am selfish, sometimes I need to be concerned, if not short term, long term issues. We see that aquatic life is going to be remarkably affected and devastated. This is from Lake Erie. Again, these are, you can see the level of algal bloom. I might not have what do we say eye catching pictures from India, but again this is pretty common in Indian what do we say lakes too. Again, Indian lakes, people are encroaching upon Indian lakes left and right. There are few lakes if any left, right. So, that is something to keep in mind, and people are not the only ones affected. Organisms like fish can be killed a lot of times. If blooms are thick enough, algae can clog the gills, reducing the ability to take in oxygen and get rid of waste. As I mentioned, you can lead to, or they can lead to dead zones. Massive amounts of algae die, and then they are going to decompose, right, because they are organic matter, and then they lead to decrease in oxygen. So, you have oxygen depletion in your particular system even during the night time, right. Again, photosynthesis, you know the principle. Algae consume considerable amount of oxygen, leading to again oxygen depletion and fish kill. This was seen in Bangalore, as in for all purposes seems like the lake was fine, but in the night or in the early morning you saw a lot of fish what do we say floating up because they were dead, and people were not sure, but again the issue was oxygen depletion in the night due to algal growth, let us say, right. So, that is something to keep in mind. Again, more colorful examples, but again as I mentioned, these are actual examples, right. And China has spent billions of dollars, but again here you can't really what do we say tackle the issue once it is already underway. The only aspect is prevention, let us see. One aspect which is remarkably prevalent in India is fertilizers, right. There is a huge fertilizer lobby, right, and obviously people push for consumption of fertilizers, and that is what we see out here, right. And one other aspect is obviously sewage treatment plant discharges and also from septic tanks, let us say, right. Now, that is the reason why we are trying to treat for or remove nitrogen and phosphorus. As I mentioned, there are no easy fixes. Sometimes people add or try to solve it and exacerbate the problem. For example, copper sulfate, though it kills the algae because it is toxic to it, it is also harmful to organisms, right. Heavy metals, and again general other aspects. But again, as I always say, education and prevention are the better strategies, and that is what we are trying to do through this course, let us say, right. And well, we do not do this, but I wanted to mention this. Recognizing what is wrong and what needs to be done to correct it is something that we can do, at least, right, by word of mouth, or by just following a decent example, as in setting the decent example, as in Bangalore again another lake frothing was observed. You can type it up or Google it, lake frothing Bangalore. You will see scenes as if you have ice out there, but it is due to excessive use of phosphorus in the detergents, a lot of detergent being used, and then you have lake frothing, and again remarkable levels of phosphorus. Again, the whole point is to let the earth be sustainable, or our life on earth be sustainable. And as I mentioned, we have algal blooms in various parts of India. I do not have the data for inland water systems, but in oceans too we have it in oceans. Nitrogen is typically the limiting nutrient, right. And we see that it is exponentially taking off. Here we have the number of high algal bloom events, and we see that it is taking off, right. That is something I just wanted to show. And in lakes, what happens is this algal blooms, let us say they fasten or hasten this particular transformation of lakes, and they become dry lands or such, let us say. You want it to be mesotrophic, but they end up being eutrophic, and this is the final stage when we let excessive nutrients coming into our water bodies, right. So, natural eutrophication takes centuries, and it leads to or it supports the aquatic ecosystem, but cultural eutrophication hastens the process, and we end up, let us say, cutting the tree branch upon which we are dependent, right. So, that is what we see out here. Let me not spend too much time, but we are talking about measuring nitrogen and phosphorus in the wastewater, because I want to remove them depending upon their concentrations. So, firstly I need to know in what forms is nitrogen present in my particular wastewater. So, NH3 or NH4 plus, right, ammonium ion or ammonia gas, right, that is one aspect. So, total ammonia nitrogen, nothing but the sum. The oxidized forms of nitrogen are nitrite and nitrate. Typically nitrite is unstable, it is usually oxidizes to nitrate, right. So, that is what we see. And then we have total inorganic nitrogen, which, as the name indicates and is self explanatory, we have the reduced forms and the oxidized forms of nitrogen. And then we have a variable that is widely used to measure nitrogen, total Kjeldahl nitrogen, and here we have for the first time both organic nitrogen and the reduced form of nitrogen, ammonia though, right. What is common out here, as I was just mentioning, in all these cases the nitrogen is in the reduced form, and organic nitrogen we are just talking about TKN minus ammonia, let us say, right, or total ammonia nitrogen. So, typically we look at this. Why am I concerned about this? Because as you can see here, we say that this is the reduced form. So, this can take in oxygen and lead to oxygen demand. So, I am typically concerned with this, right, and also we obviously are looking at the removal of nitrogen. So, how do I measure this TKN, let us say, right. So, typically I need to convert this fraction of organic nitrogen into ammonia. So, I am going to apply heat and acid, typically acidic conditions, and I am going to this is called digestion, and then I will measure this particular NH3 and NH4 plus or the converted forms of ammonia. So, how do I measure this organic nitrogen? It is not that I am going to take the difference or little difference of these two particular parameters, but I can see to it that the pH is changed, right. We know the pH pK relationship, and I can see to it that I can see to it that this ammonia changes phase from the aqueous phase to the gaseous phase, and typically that is done during boiling. So, first I am going to boil it and then see to it that the conditions are such that ammonia leaves the aqueous phase and goes into the gaseous phase, right. Then I am just left with the organic nitrogen, which I digest, right, in acidic conditions, and then measure the nitrogen content, and that will give me organic nitrogen. But in TKN, I am not going to boil it or see to it that I am not going to see to it that NH3 and NH4 plus leave the system, right. That is the primary difference. Let me move on. So, in nitrogen, as I mentioned, organic nitrogen is a key component, and microbes obviously are going to break it down such that or convert it into ammonia before using it for cell synthesis and so on and so forth. With respect to the other particular nutrient, right, we have phosphorus. So, there are three primary forms A, B and C of phosphorus: orthophosphates, right, and when I am talking about this, it is H3PO4. Typically it can't be in H3PO4, typically pH is not so low, H2PO4 minus, HPO4 2 minus and PO4 3 minus, right. And then I have the polyphosphates, polyphosphates, relatively more complex with 2 phosphorus or such or more, and then I have organic forms of phosphorus, let us see. But typically microbes take a lot of time to what do we say, make them soluble so that they can be utilized. So, unlike organic nitrogen, organic phosphates, they typically stay in the solution, and polyphosphates, let us say, I think we call them acid hydrolyzable, right. So, typically we are concerned with orthophosphates, not phosphates. We look at orthophosphates because they are readily consumed or assimilated by the relevant microbes, but organic phosphates not really. So, they can persist in the sludge too, right. So, that is something to keep in mind, right. With that, I will end my session, and we will look at pathogens in the next session, and as usual I thank you for your patience.